Welcome back to another episode of Agentic AI, the future of intelligent systems. I'm your host, Naveen Balani, and in this episode, I want to talk about something that's been on my mind a lot lately. What it actually costs to run an agent in production, not just in dollars, in watts, and in carbon. Specifically, I want to walk you through the work I've been doing on agent architectures, what it takes to design these systems without waste. This is essentially the shape of a talk I gave recently at Google I/O. But here I want to go a little longer, share some of the numbers I've measured myself, and tell you what I've actually built to test whether the discipline holds up. Let's get into it. Before we deploy 1,000 agents, there's a question I think we should all be sitting with. Whether you're shipping one agent or 1,000, whether it runs once a day or it never sleeps, the question is the same. What does it actually cost to run an agent at production scale? Not just the API bill, the full bill. Dollars, watts, carbon. Most teams I talk to can't answer that question. And it's not because the answer is unknowable. It isn't. It's because nobody is measuring. And what I've been finding doing this work over the last year is that the answer is almost always much higher than it needs to be. 10 times, 20 times, sometimes higher. And here's the part that matters. Those three costs, money and energy and carbon, they compound. Every wasted token costs you dollars and watts and grams of CO2 at the same moment, which turns out to be very good news. And I'll come back to why. Let me set the scale for you. Three numbers to have in mind: a single chat query, roughly 3 to 10 times the electricity of a typical web search. A coding agent session, the kind of thing you spin up for a debugging task or a code review. It can consume around 138 times the energy of a single chat query. That figure comes from more recent analysis, and it makes sense when you think about what an agent session actually does. Dozens of model calls, tool invocations, retries, it multiplies fast and zooming all the way out. Global data center electricity demand, per the IEA's latest energy and AI report, is set to more than double by 2030, from 415 terawatt hours to 945. None of those is comforting on its own, but taken together and combined with the fact that we're deploying agents at unprecedented speed, trillions of tokens a month move through frontier models today. Modern agent runtimes now support long running operations up to 7 days. You start to see the shape of the situation. Agents that don't sleep, electricity demand that won't stop climbing, and no measurement layer between us and it. So, where does the waste actually come from? Here's what I've noticed. If I sit down with a team and look at their agent code, the waste is almost always in the same six places. Every agent, whatever it does, moves through these six stages: goal ingestion, planning, tool and model selection, action execution, reflection, and memory, and waste lives in every single one. Goal ingestion: you take an ambiguous prompt and hand it straight to the largest, most expensive model. Planning: the agent plans in a loop with no depth cap, and the same prompt gets sent over and over with tiny variations. Tool and model selection: the largest model gets used for every subtask, even the ones that could run on something 20 times cheaper. Action execution: always on infrastructure burning idle compute, full documents resent with every call, verbose outputs nobody asked for. Reflection: infinite retry loops with no exit criteria and no calibrated confidence threshold. Memory: every prompt and every response stored indefinitely, then dumped back into the next request without filtering. And here's what makes this so hard to fix: by looking at any one stage. The leaks compound. A verbose plan in stage 2 makes tool calls in stage 4 longer. Those longer tool calls make memories at stage 6 larger. Those larger memories make the next run's prompt bigger. Every stage is a leak, and every leak feeds the next one. Now, here's what I keep noticing watching teams try to fix this. Most reasoning about agent cost happens qualitatively. I hear things like, this pattern feels lean, that model is probably cheaper. We'll optimize later. But cost, energy, and carbon aren't intuitions, they're numbers, measurable, attributable, comparable. And without a measurement layer, every architectural choice you make is a guess, and every optimization you claim is unfalsifiable. It's like doing performance work without a profiler. You might be right, you might be wrong, but you can't tell. And you certainly can't defend the number in front of a CFO. What we need is three things: a standard unit for the carbon impact of an agent task, a measurement method that uses telemetry we already collect, and an open standard so results are comparable across teams and clouds and vendors. That isn't a wish list, it exists. It's called software carbon intensity, SCI for short. It's an ISO standard maintained by the Green Software Foundation. The formula is one line, and I want to say it slowly because it's the spine of everything else in this episode. SCI equals E times I plus M all per hour. E is the energy your software consumes in kilowatt hours. I is the carbon intensity of the grid powering it, grams of CO2 per kilowatt hour. M is the embodied hardware carbon, amortized per request. And R, this is the important one, R is the functional unit, the unit of work you're measuring against. For an agent, R is per task, per rebalance, per query, per decision. The part SCI insists on, which most carbon metrics don't, is reduction, not offset. You can't offset your way out of an SCI number. You have to actually drive it down. And that's a discipline shift as much as a measurement shift. No buying credits, no hand waving. The Green Software Foundation is now extending this specifically for AI workloads. We call it SCI for AI. It addresses the questions the base standard leaves open when the software you're measuring is inference itself. What a functional unit actually means for a token generating system. How to attribute embodied carbon across shared accelerators, and how to make training cost and inference cost comparable. That extension is what I've been applying to agents. It's still evolving, but the shape is there. Now, before I move into specific platform components, one important note I want to make. Everything I've discussed so far, the 6 stages, the 8 levers, the SCI methodology, all of it is universal. It applies whether you're building on Google Cloud, on AWS, on Azure, or on any other vendor. For the rest of this episode, I'll use Google Cloud as my reference implementation because that's what I've been building on most recently, and the service names map cleanly to the concepts. But every service I mention has an equivalent on the other major clouds, and every lean lever I describe translates. Consider Google Cloud a specific instance of the general discipline, not the discipline itself. If you're on AWS, you'll find Bedrock and Lambda give you the same primitives. On Azure, it's AI Foundry and container apps. Same shape, different naming. So take the ideas as universal and take the tooling I name as illustrative. So SCI gives you the equation. How do you feed it? On Google Cloud, all 4 inputs are already available. And this is where the platform ergonomics start to matter. E, the energy, comes from the observability you already collect. Token counts, vCPU seconds, latency traces, all flowing through Cloud Trace, Cloud Monitoring, and Cloud Logging. And with the latest agent runtime release, OpenTelemetry tracing is default on for ADK agents. You don't wire it up, it's just there. I, the grid intensity, comes from two sources. Google publishes per region carbon disclosures, which give you an average intensity per region. And you can layer that with the electricity maps API to get real time marginal intensity, which is more accurate for the question of should I run this now or later. M, the embodied carbon, comes from Google's own accelerator lifecycle data, amortized per request. TPU and GPU embodied emissions divided by expected lifetime request count. And I'll be honest, this is where the biggest error bars sit in the calculation. And R, the functional unit, is whatever you define in agent evaluation per rebalance, per lookup, per decision. UI all for through an open telemetry exporter, and out the other end comes a single metric per task. I call it SciScore, grams of CO2 equivalent per task. The clean thing about it is that it's joinable. Same schema, same task, ID with cost, latency, and quality. So the same dashboard that shows your P95 latency now shows your carbon per task. That's the spine. Everything else in this episode is about how to drive that number down. The discipline of driving that number down is what I call Lean Agentic AI. It's not a checklist, it's a way of designing agents to be efficient by design across cost and energy and carbon. And it's structured around the same 6 stages I just walked you through. Underneath those stages, there are 8 recurring levers that come up over and over again. Model selection, smallest model that meets the bar, prompt design, structured, templated, minimal, context window, only what's needed, never more. Tool usage, conditional, metadata driven, reflection caps, bounded retries with calibrate confidence, memory storage, high signal only with retention policies, execution timing, carbon aware scheduling, and regions, and observability, measure everything, attribute it. These 8 are what I look for when I'm reviewing an agent design. If more than half of them aren't being addressed, you have room to move. Now, let me give you a quick orientation on the Google Cloud side because a lot has shifted recently. Vertex AI is now called Gemini Enterprise Agent Platform. That rebrand happened at Cloud Next earlier this year. It's organized into 4 pillars. Build is where you compose agents. Agent Studio, the ADK with its graph framework. The Agent CLI for natural language scaffolding. Model Garden, scale is where they run. Agent Runtime with those 7-day operations. Memory Bank, sessions, batch and event agents. Code execution as a managed service. Govern is where you control them. Agent Registry, Agent Gateway, Agent Identity, Model Armor, and the new Agent Payments Protocol. And Optimize is where you close the loop. Agent Evaluation, Simulation, Observability, and the new Skill Registry. Most of what I just named landed in the last 2 releases, Cloud Next and I/O 2026. So if you looked at this platform a year ago, it's meaningfully different now. And every lean lever I mentioned maps to specific services in here. Let me give you a concrete case because abstract discipline talk only goes so far. The example I've been using and the one I built a runnable demo for is an ESG portfolio rebalancing agent, a wealth management context. The user types, one sentence, rebalance, ESG portfolio for client 84721. Behind that single sentence, quite a lot has to happen. The agent has to interpret the intent and extract the client scope. It has to plan a chain of steps, fetch the data, score against ESG criteria, calculate risk, propose an allocation, summarize for the client. It has to select the right scoring models, ESG filters, and risk tools dynamically. It has to execute the rebalancing logic. It has to reflect on confidence and retry where constraints don't hold. And it has to remember what was accepted for next time. Financial services, multi-tool, multi-model. I built it twice. the default version. And I want to be clear about this. It's not a straw man. It's what first draft agent code honestly looks like. It sends every prompt to the pro tier model: full policy document, full portfolio, full client history, injected as context on every single call. 5 sequential model calls to the work, even though 3 of those steps are really just table math: adding up weights, checking caps, deterministic work. And when the synthesis output comes back as free form prose and the JSON parse fails, the code pays again to retry, with the failed answer stacked on top of the already huge prompt. The lean version is fundamentally different. It's a graph. Each step is a node, and each node is either code or a model, whichever the step actually needs. A small, fast model flashlight classifies the request first in about 45 tokens. Pure Python parses the portfolio and checks the policy caps. 0 tokens, because none of that ever needed a language model in the first place. A conditional router decides whether we even need to synthesize. For a fully compliant portfolio, we short circuit and never invoke the synthesis model at all. The unchanging policy document sits in an explicit context cache, billed at roughly a tenth of the normal input rate. One mid-tier model called Gemini Flash synthesizes the recommendation with the output schema constrained so parsing cannot fail. And there's no retry because the failure mode was designed out, not handled better. Now, here's where a podcast lets me be honest in a way a stage talk doesn't quite allow. Let me tell you what I actually measured, and let me also tell you what those numbers mean and what they don't. On one live run against the real model API, the default version made 6 model calls and took about 4 minutes of wall clock time. The lean version made 2, and roughly 90% of its input came out of the context cache. Cost per task, energy per task, carbon per task, all three moved in the same direction and roughly the same amount. I'd put it in the neighborhood of 85 to 90% reduction across all three currencies on the same task, producing the same recommendation. I want to be direct about what those numbers are and aren't. The token counts are real, captured from actual API responses. The dollar and carbon figures are computed. I feed those tokens through pricing, energy, and grid intensity tables that are directionally correct but not audit grade. And any straight line extrapolation to an annual fleet cost assumes a steady state no real fleet has. Treat everything as a calibration mark, not an invoice. What holds up unambiguously is the shape of the result. The call count collapse from 6 to 2, the input token collapse of over 90%, no retry, one cached call doing the work of 6 uncatched ones. That shape is real and it's reproducible. The exact digits will move with your prices, your region, and your models. There was one detail from those runs that I keep coming back to, and I want to share it because I think it's the whole discipline in miniature. In one of my early runs of the default version, the platform's implicit caching spontaneously kicked in on the retry. The infrastructure noticed that I was resending the same giant prefix seconds later, and it quietly discounted a big chunk of it without me asking. It effectively tried to rescue my wasteful code. In the next run of the exact same code, that discount didn't fire at all. That's implicit efficiency for you. Opportunistic. Sometimes the platform helps you, sometimes it doesn't. The lean version doesn't hope for a discount. It creates one every time, deliberately. And that's what engineered versus wished for looks like in practice. There's one more lever I want to mention because it lives outside the 6 stages, and it's the one that's most specific to which cloud you're on. It's about when and where you run. 3 sublevers here: region, place batch, and event driven workloads in regions with high carbon free energy percentages. Cloud providers Publish this per region quarterly. Pick high, defer low, time, use an event bus plus batch agents to defer non urgent subtasks and trigger them on low grid intensity windows via the Electricity Maps API. And triage. Accept that interactive agents can't be moved, but recognize that even a real time agent has parts of its workload that can wait an hour. Split urgent from deferred and route accordingly. For a portfolio manager, running 20,000 rebalances a day, where two-thirds are advisory or scheduled, this split and defer pattern can shift the bulk of the compute into batch pricing on low carbon hour execution. 50% off on those tokens, plus a meaningful grid intensity reduction. On top of that, real time stays instant. The heavy work waits for green. Now, I want to shift for a moment because everything I've talked about so far is technically achievable today on any major cloud with the platform pieces we walked through. None of this is a research project, it's configuration. But what I've seen over and over is that the failure mode isn't technical, it's organizational. Lean Agentic AI is a people change first and a systems change second. It requires executive advocacy. Cost and carbon has to be a stated leadership priority, not a footnote. It requires metrics, size score per task tracked alongside latency and quality on every agent. It requires a mindset shift. Engineering teams rewarding lean design as much as feature velocity. It requires enablement, teams trained on what lean actually means in each stage. It requires cross disciplinary collaboration, sustainability, FinOps, and engineering sharing a single dashboard. And it requires ongoing discipline. SCI scores reviewed quarterly, regressions treated like performance bugs. The teams I've seen succeed at this don't have better engineers, they have a shared definition of good. If you're listening to this and thinking, okay, where do I start? Let me leave you with something concrete. Here are the moves you can make in the next week. Route through a small, fast model first, flashlight, or its equivalent on your platform, and only escalate to the largest tier when confidence demands it. Define your agent graph topology explicitly with a bounded max depth and scoped subagent state. Deploy on a serverless agent runtime for scale to zero. Turn on context caching for any reuse policy or instruction document. Move overnight or batch jobs to your provider's batch inference API. That's a flat 50% off on most platforms, no other conditions. Configure your memory store with event triggered generation so you only store what was accepted. Set graph level retry caps with confidence thresholds calibrated through your evaluation framework. Enable agent observability and start emitting an SCI score metric per task. And place batch workloads in high clean energy regions, deferring non urgent work to low carbon windows. None of these is a research project. Each is a configuration change. And the result by end of the week is a baseline size score, a measurable trajectory, and an architecture you can defend in front of a CFO. Let me leave you with one line that, if you take nothing else from this episode, I want you to hold on to. You wouldn't send a Ferrari to deliver a pizza. Sure, it could. But would you? Think big. Design and deploy lean. That's what this podcast is about. That's what Lean Agentic AI as a discipline is about. Build agents that earn their watts. That's a wrap on this episode. If you want to go deeper on any of this, the demo I mentioned is open source. You can run it in simulation mode with no credentials or in live mode against your own API key. The methodology follows ISO IEC 21031. There's a book, Lean Agentic AI, Minimizing Cost, Carbon, and Complexity at leanagenticai.com, and more on the standard itself at the Green Software Foundation greensoftware.foundation. If this episode resonated, share it with a colleague who's building agents. And if you're seeing patterns in your own agent fleet that I didn't cover, good or bad, I genuinely love to hear about them. You'll find my contact in the show notes. Thanks for listening. I'm Naveen Balani. Until next time, build agents that earn their watts.